Have you ever looked up at the night sky and wondered about the mysteries of the universe? One of the most fascinating and mysterious objects in space is the black hole. Let's explore what black holes are, how they were discovered, and why they are so important in our understanding of the cosmos. Don't worry, we'll keep it simple and easy to follow. Let's start with the basics. A black hole is a place in space where gravity is so strong that nothing, not even light, can escape. Imagine a giant vacuum cleaner in space, but instead of sucking up dust, it sucks up everything around it, including stars, planets, and even light. That is called a black hole. Black holes are invisible because no light can escape from them. But scientists can detect them by observing how they affect the things around them. For example, if a star is orbiting an invisible object and behaving strangely, it might be because of a black hole. Now, let's talk about some properties of black holes. Every black hole has something called an event horizon. This is the point of no return. Once something crosses the event horizon, it's gone forever. Even light can't escape. Inside the black hole, there's something called a singularity. This is the center of the black hole, where all the matter is crushed into an infinitely tiny point. It is like squeezing the entire Earth into the size of a marble. Sounds crazy, right? But it is true, though there are a lot of myths and misconceptions about black holes. Let's clear some of them up. First, black holes are not cosmic vacuum cleaners that go around sucking up everything in the universe. They only pull in things that come too close. If you replaced our sun with a black hole of the same mass, the Earth would keep orbiting it just like it does now. We wouldn't get sucked in. Another misconception is that black holes are portals to other universes or dimensions. While this idea is fun to think about, there's no scientific evidence to support it. Black holes are more about extreme gravity than science fiction. Now, let's take a step back in time and see how black holes were discovered. The story begins with one of the greatest scientists of all time, Albert Einstein. In 1915, Einstein published his theory of general relativity. This theory explained how gravity works. According to Einstein, gravity isn't just a force. It's the bending of space and time by massive objects. Think of it like placing a heavy ball on a trampoline. The ball creates a dent, and smaller objects roll toward it. That's how gravity works. Einstein's equations predicted the existence of black holes, but even he didn't fully believe they could exist. It took decades of research and discovery to prove him right. Long before Einstein, in the 18th century, an English scientist named John Michell had an interesting idea. He wondered what would happen if a star was so massive and dense that its gravity would prevent light from escaping. He called this idea a dark star. Michell's concept was ahead of its time, but it laid the groundwork for future discoveries. Now, moving forward to the 20th century, an Indian-American astrophysicist named Subramanian Chandrasekhar made a groundbreaking discovery. He studied what happens to stars when they run out of fuel. Stars are like giant nuclear reactors. They burn fuel to produce light and heat. But when the fuel runs out, the star collapses under its own gravity. He calculated if a star is more than about 1.4 times the mass of our sun, it won't just collapse into a small, dense object like a white dwarf. Instead, it will keep collapsing until it forms a black hole. This number is now called the Chandrasekhar limit. His work was so important that he won the Nobel Prize in Physics in 1983. So, how do black holes actually form? Most black holes are born from the death of massive stars. When a star which is bigger than our sun runs out of fuel, it explodes in a supernova. The outer layers of the star are blasted into space and the core collapses. If the core is massive enough, it will keep collapsing until it forms a black hole. There are also supermassive black holes, which are millions or even billions of times more massive than our sun. These are found at the centers of galaxies, including our own Milky Way. Scientists are still trying to figure out how these supermassive black holes form. One theory is that they grow over time by merging with other black holes and swallowing stars and gas. Black holes might seem like strange and distant objects, but they play a crucial role in the universe. They help us understand the laws of physics. For example, studying black holes can teach us about gravity and spacetime. They also help us learn how galaxies form and evolve. In 2019, scientists made history by capturing the first-ever image of a black hole. Using a network of telescopes called the Event Horizon Telescope, they took a picture of a supermassive black hole at the center of a galaxy called M87. The image showed a bright ring of light around a dark shadow, which was the black hole's event horizon. This was a huge achievement and gave us a glimpse into the mysterious world of black holes. The story of the first black hole discovery is a fascinating journey that spans centuries. It is a tale of brilliant minds, groundbreaking theories, and the relentless pursuit of knowledge. Let's dive into how humanity came to discover these mysterious objects in space. The idea of black holes did not just appear overnight. It started with small clues and curious observations. Scientists like Albert Einstein and Jean-Michel knew that black holes exist, but could not prove its existence due to lack of technological advancement. After them, another scientist named Robert Oppenheimer and his student Hartland Snyder used Einstein's equations. They showed how a massive star could collapse into a black hole. Later, Oppenheimer became famous for his work on the atomic bomb. All of their work was groundbreaking, but it was still just a theory. No one had actually found a black hole yet. For decades, black holes remained a mystery. Scientists knew they could exist, but they had no way to detect them. After all, black holes are invisible. They don't emit light or any other form of radiation that we can see. So, how do you find something you can't see? The answer is really simple. A black hole can be found by observing its surroundings. Black holes have such strong gravity that they pull in nearby gas, dust, and even stars. As these materials spiral into the black hole, they heat up and emit X-rays. Scientists realized that if they could detect these X-rays, they might be able to find a black hole. In the 1960s, astronomers began using X-ray telescopes to search for black holes. One of the first major discoveries came in 1964, when scientists detected a strange X-ray source in the constellation Cygnus. They named it Cygnus X1. In the beginning, they weren't not sure what it was, but as they studied it more closely, they noticed something unusual. Cygnus X1 was part of a binary system. Scientists saw two objects orbiting each other. One was a bright blue star, and the other was invisible but had a strong gravitational pull. The invisible object was pulling gas from the star, and after the gas spiraled inward, it emitted X-rays. This was exactly what scientists expected to see if there was a black hole. For years, Cygnus X1 remained the best candidate for a black hole, but scientists needed more evidence to confirm it. In the 1970s, they used advanced telescopes and mathematical models to study the system in detail. They calculated that the invisible object had to be at least 10 times more massive than the Sun. This was far too massive to be a neutron star or any other known object. The only explanation was that it was a black hole. In 1971, the scientific community officially recognized it as the first black hole ever discovered. This was a monumental moment in astronomy. It proved that black holes weren't just theoretical objects, they were real, and they existed in our universe. The discovery of Cygnus X1 opened the door to a new era of black hole research. It showed scientists where and how to look for black holes. Over the years, they've discovered many more black holes, both small and supermassive. Each discovery has helped us learn more about these mysterious objects and their role in the universe. After recognition, Cygnus also became a cultural icon. It inspired songs, books, and even episodes of science fiction shows. But more importantly, it reminded us of the power of human curiosity and the importance of exploring the unknown. We discovered the first black hole in 1971, but we could not capture an image of a black hole until 2019. It was captured using a network of telescopes called the Event Horizon Telescope. Scientists captured an image of a supermassive black hole at the center of a galaxy called M87. The image showed a bright ring of light surrounding a dark shadow. That is the black hole's event horizon. This was a historic moment and a testament to how far we've come in understanding black holes. The discovery of the first black hole, Cygnus X1, was a milestone in science. It took centuries of theories, calculations, and observations to finally prove that black holes exist. Now, we know that black holes are not just rare anomalies, they are a fundamental part of the universe. They shape galaxies, influence the movement of stars, and challenge our understanding of physics. Black hole is one of the most mysterious things of the universe. Every year, new discoveries makes us feel surprised. Though one thing is certain, the journey to understand these mysterious objects is far from over. Now let's talk about supermassive black holes and their role in galaxies. Supermassive black holes are the cosmic giants that reside at the centers of large galaxies. These black holes have masses ranging from millions to billions of times that of the Sun. Their presence is directly connected to the formation and evolution of galaxies. Astronomers have discovered that the mass of a supermassive black hole has a strong relation with the mass of the galaxy. This relationship is known as the M-sigma relation. This suggests that supermassive black holes and their host galaxies grow together. They influence each other for billions of years. The black hole plays a key role during the galaxy formation process. It regulates star formation through its powerful outflows of energy and matter. Black hole forms an accretion disk when it actively swallows material from its surroundings. It heats up to millions of degrees. It also emits immense amounts of energy in the form of light, X-rays, and high-energy particles. These particles reach far beyond the galaxy and sweep up gas. By this process, it limits the amount of material available for star formation. This feedback mechanism helps shape the galaxy's structure and star-forming activity. It makes the supermassive black hole central to the life cycles of galaxies. Black hole mergers are another fascinating aspect of galaxy evolution. When two galaxies collide, their central black holes eventually merge. This process produces ripples in spacetime known as gravitational waves. It can be detected by observatories like LIGO and Virgo. Such mergers also lead to the formation of even larger supermassive black holes. These mergers help to grow the galaxy. Now let's talk about a supermassive black hole of our own galaxy. A supermassive black hole named Sagittarius A, which is located at the heart of our own Milky Way galaxy. It is located about 26,000 light-years from Earth. Compared to our Sun, this black hole has a mass of approximately 4 million times. It is a relatively quiet black hole compared to the actively feeding supermassive black holes found in other galaxies. However, it has a profound influence on its surroundings. Stars and gas clouds orbit this black hole at incredible speed. This provides indirect evidence of its presence. In 2020, the Event Horizon Telescope captured the first-ever image of a black hole in the galaxy M87. Then it turned its focus to Sagittarius A. Now it aims to reveal its secrets. Observing Sagittarius is challenging due to its smaller size and rapid variability compared to other supermassive black holes. Nevertheless, it remains as an important target for understanding the physics of black holes and their interactions with their environments. The discovery and study of Sagittarius have also led to some groundbreaking achievements in astrophysics. In 2020, The Nobel Prize in Physics was awarded to Reinhard Genzel and Andrea for their work tracking the orbits of stars near the galactic center. Their work provided proof of a supermassive black hole at the heart of the Milky Way. Supermassive black holes like Sagittarius are not just fascinating cosmic phenomena. It will help us understand the universe. By studying these giants, astronomers continue to uncover the profound connections between black holes and galaxies. The presence of supermassive black holes also provides insights into the large-scale structure of the universe. Galaxy clusters and the largest gravitationally bound systems in the cosmos have a massive black hole at their cores. These central black holes influence the cluster medium. It produces hot gas that fills the space between galaxies through their energetic outbursts. Such activity regulates the cooling of gas, which affects star formation rates across the cluster. Another fascinating aspect is the study of quasars. It is also powered by supermassive black holes. Quasars are some of the brightest objects in the universe. Quasars can outshine entire galaxies. Observing quasars allows astronomers to study black holes and galaxy evolution in the early universe, as many quasars date back to the first few billion years after the Big Bang. They serve as cosmic lighthouses. It helps scientists map the distribution of matter across the universe. Finally, supermassive black holes also play a role in shaping the cosmic environments around them. For example, their immense gravity influences the motion of stars, gas, and other celestial objects. It creates dynamic and sometimes chaotic regions in galactic centers. Sagittarius is surrounded by a dense cluster of stars, including young and massive ones that have formed in the extreme conditions near the black hole. These stars offer valuable clues about the nature of supermassive black holes and their immediate environments. The study of supermassive black holes is not only a journey into the mysteries of these enigmatic objects, but also a deeper exploration of the universe itself. They play an important role as cosmic architects in the cosmos. They shape the formation and evolution of galaxies. It highlights their importance in the grand narrative of the cosmos. Supermassive black holes remain key players in the ongoing story of the universe's growth and complexity. Now we will discuss relation between multiverse theories and black holes. One of the most exciting ideas is that black holes could be portals to alternate universes in a multiverse framework. The multiverse hypothesis suggests that our universe is just one of many, each with its own unique physical laws and constants. Some physicists speculate that the interior of a black hole could lead to a new universe. This idea stems from general relativity, which predicts that the collapse of matter into a singularity could result in the formation of a new spacetime region. If this is true, every black hole in our universe might be the seed of a new universe. Our own universe could have originated from a black hole in another. While there is currently no way to test this hypothesis, it provides a fascinating perspective on the interconnectedness of the cosmos and the potential for infinite cycles of creation. Another hypothesis suggests existence of wormhole in the universe. It says we can travel really fast through space using wormholes as theoretical bridges. This hypothesis is closely related to the idea of black holes. Wormholes are hypothetical shortcuts through space-time that could connect distant regions of our universe or even different universes. Wormholes, also called Einstein-Rosen bridges, are solutions to Einstein's equations of general relativity. This describes a tunnel-like structure linking two separate points in space-time. In theory, a black hole could serve as the entrance to a wormhole, with the other end opening elsewhere in the universe. However, traveling through a wormhole would require overcoming several challenges. First, the immense gravitational forces near a black hole would likely destroy any object attempting to enter. Second, wormholes are predicted to be highly unstable, collapsing almost instantly unless stabilized by an exotic form of matter with negative energy. Despite these challenges, the possibility of using black holes and wormholes as cosmic bridges remains an area of active research. Scientists like Kip Thorne have explored the theoretical foundations of wormholes, and while no evidence has been found for their existence, they remain a tantalizing prospect for future exploration. The speculative ideas surrounding black holes push the boundaries of human imagination and scientific understanding. Whether as sources of boundless energy or as gateways to other universes, black holes challenge us to think beyond the limitations of our current technology and knowledge. Now let's discuss about Sagittarius A. At the center of our Milky Way galaxy, there is a mysterious and incredibly dense object known as Sagittarius A. For decades, astronomers have suspected that this object is a supermassive black hole. The motions of stars orbiting it provide some of the strongest evidence for this claim. Since 1995, scientists have been tracking the movements of 90 stars near the galactic center. These stars are orbiting an invisible object that coincides with the radio source Sagittarius A. By studying its path, astronomers have been able to prove the presence of an extremely massive and compact object. In 1998, researchers calculated that the star's motions. It proved the existence of an object that has 2.6 million solar mass. That was packed into a region smaller than only 0.02 light-years across. Over time, one of the orbiting stars called S2 completed a full orbit of Sagittarius A. Astronomers refined their calculations at that time. After the new calculation, they estimated that the central object has a mass of 4.3 million solar masses and is confined to a region smaller than 0.002 light-years in radius. While this size is still too large to confirm that the object is smaller than its Schwarzschild radius, this evidence strongly suggests that Sagittarius is indeed a supermassive black hole. No other known object could pack so much mass into such a tiny space. Additionally, there are hints that this object might have an event horizon. Now we will discuss about the black hole information paradox. It is one of the most profound and enduring puzzles in modern theoretical physics, challenging our understanding of the fundamental laws governing the universe. At its core, the paradox arises from the apparent conflict between two of the most successful frameworks in physics. They are quantum mechanics and general relativity. While quantum mechanics governs the behavior of particles and fields on the smallest scales, general relativity describes the gravitational force and the large-scale structure of spacetime. The paradox emerges when these two theories are applied simultaneously to black holes, leading to a contradiction that has puzzled physicists for decades. So let's talk about the origin of the paradox. The paradox was first brought to light by Stephen Hawking in the 1970s through his groundbreaking work on black hole radiation. Now it is known as Hawking radiation. According to classical general relativity, a black hole is a region of spacetime where gravity is so intense that nothing, not even light, can escape its pull. The boundary of this region is called the event horizon. Once matter or energy crosses the event horizon, it is irretrievably lost to the outside universe. This description suggests that black holes are simple objects, characterized only by their mass, charge, and angular momentum, a concept known as the no-hair theorem. However, Hawking's discovery complicated this picture. Using quantum field theory in curved spacetime, he showed that black holes are not entirely black. Due to quantum effects near the event horizon, black holes can emit radiation and gradually lose mass over time, a process now referred to as Hawking radiation. This radiation is thermal, meaning it carries no information about the matter that originally formed the black hole. Over time, as the black hole radiates away its mass, it eventually evaporates completely, leaving behind only thermal radiation. This presents a significant problem. What happens to the information about the matter that fell into the black hole? According to quantum mechanics, information about the state of a physical system must always be preserved. This principle, known as unitarity, is a cornerstone of quantum theory. However, if a black hole evaporates completely and leaves behind only featureless thermal radiation, it appears that the information about the infalling matter is lost forever. This contradiction between the principles of quantum mechanics and the behavior of black holes is the essence of the black hole information paradox. Moving to the next topic, which is why the paradox matters. The black hole information paradox is not merely a technical issue. It strikes at the heart of our understanding of the universe. If information can indeed be lost in black holes, it would require a radical revision of quantum mechanics, one of the most well-tested and successful theories in the history of science. On the other hand, if information is preserved, it must somehow escape the black hole, which seems impossible given our current understanding of general relativity. Resolving the paradox is crucial for developing a consistent theory of quantum gravity, which would unify quantum mechanics and general relativity into a single framework. The paradox also has deep implications for the nature of spacetime and the fundamental principles of physics. For example, it challenges the notion of locality, the idea that physical processes are influenced only by their immediate surroundings. If information can escape a black hole, it must somehow be encoded in a non-local way, suggesting that spacetime itself may have a more complex structure than previously thought. Additionally, the paradox raises questions about the nature of entropy and the second law of thermodynamics, as black holes are known to have entropy proportional to their surface area. Now let's talk about proposed solutions to the paradox. Over the years, physicists have proposed numerous solutions to the black hole information paradox. Each offers a different perspective on how information might be preserved. While none of these solutions have been universally accepted, though they have significantly advanced our understanding of the problem and inspired new avenues of research. The first solution suggests information is encoded in Hawking radiation. One of the most promising ideas is that the information about the infalling matter is not lost, but is instead encoded in the Hawking radiation itself. Although the radiation appears thermal and featureless at first glance, subtle correlations between the emitted particles might carry the necessary information. This idea is supported by calculations in string theory and other approaches to quantum gravity, which suggests that the radiation is not perfectly thermal but contains tiny deviations that encode the lost information. If this is the case, the information would gradually leak out as the black hole evaporates, preserving unitarity. The second solution is based on the holographic principle and CFT correspondence. Major breakthrough in addressing the paradox came from the holographic principle. It suggests that all the information contained within a volume of space can be represented as a theory on the boundary of that space. This idea gave a concrete mathematical foundation through the CFT correspondence. According to the holographic principle, the information about the matter that falls into a black hole is not lost, but is instead encoded on the event horizon. As the black hole evaporates, this information is transferred to the Hawking radiation, preserving unitarity. The CFT correspondence provides a powerful tool for studying this process, as it allows physicists to analyze the behavior of black holes using the well-understood rules of quantum field theory. The third solution is based on black hole remnants. Some physicists have proposed that black holes do not evaporate completely, but it leave behind stable remnants that contain the missing information. These remnants would be extremely small and massive, with properties that prevent them from radiating further. While this idea avoids the loss of information, it introduces new problems, such as the need for an infinite number of remnant states to account for all possible initial conditions of the black hole. This would violate the principles of quantum mechanics and is generally considered an unattractive solution. The next solution is based on firewalls and the AMPS paradox. In 2012, physicists Ahmed Almhiri, Donald Merolf, Joseph Polchinski, and James Sully proposed a radical solution to the paradox, suggesting that the event horizon of a black hole is not a smooth region of spacetime, but is instead a highly energetic firewall that destroys any infalling matter. This idea was motivated by the need to preserve the purity of Hawking radiation and avoid contradictions with quantum mechanics. However, The firewall hypothesis has been controversial, as it conflicts with the equivalence principle of general relativity, which states that an observer falling into a black hole should not notice anything unusual at the event horizon. The last solution is based on fuzzballs and string theory. String theory offers another potential resolution through the concept of fuzzballs. According to this idea, black holes are not smooth and featureless objects, but are instead composed of a tangled web of strings and branes that extend beyond the event horizon. This structure would prevent the formation of a true singularity and allow information to be preserved within the black hole. While the fuzzball proposal is still speculative, it provides a compelling picture of how quantum effects might alter the classical description of black holes. Now let's discuss current status and future directions of the information paradox. Despite decades of research, the black hole information paradox remains unresolved. Each proposed solution has its strengths and weaknesses, and none have yet achieved consensus within the physics community. However, the paradox has driven significant progress in our understanding of quantum gravity, black holes, and the nature of spacetime. For example, the study of Hawking radiation and the holographic principle has led to new insights into the relationship between gravity and quantum field theory, while the firewall hypothesis has sparked renewed interest in the foundations of general relativity. One of the key challenges in resolving the paradox is the lack of experimental evidence. Black holes are notoriously difficult to study directly, and Hawking radiation is too faint to be detected with current technology. However, advances in observational astronomy, such as the detection of gravitational waves by LIGO and Virgo, offer new opportunities to test theoretical ideas about black holes. Additionally, analog black holes in laboratory settings, such as those created using Bose-Einstein condensates, provide a way to study Hawking radiation and related phenomena in a controlled environment. In the coming years, the development of a complete theory of quantum gravity will be essential for resolving the black hole information paradox. Whether this theory takes the form of string theory or some other framework, it must reconcile the principles of quantum mechanics with the behavior of black holes. Until then, the paradox will continue to inspire and challenge physicists, driving us closer to a deeper understanding of the universe. Now let's talk about relation between black holes and time. One of the most mind-bending effects of black holes is their impact on time. Near a black hole, the intense gravitational field warps spacetime. It is so staring that time itself slows down for an observer close to the black hole, compared to someone far away. This phenomenon is known as gravitational time dilation. It is a direct consequence of Einstein's general theory of relativity. As you approach the event horizon of a black hole, time appears to stretch out infinitely. To a distant observer, an object falling into the black hole would seem to slow down and hover near the event horizon, never actually crossing it. The light emitted from the object becomes increasingly redshifted, eventually fading into darkness as it reaches the infrared and radio spectrum. Time continues normally from the perspective of the object. It crosses the event horizon without noticing anything unusual at that precise moment. An extreme example of this effect occurs near supermassive black hole. Generally, they are found at the center of the galaxies. Because their event horizons are larger, the effects of gravitational time dilation are more pronounced and occur over a greater distance. If you were to orbit near such a black hole while your friend remained far away, you would age much more slowly than your friend. In science fiction, this concept is famously depicted in movies like Interstellar, where an hour spent near a massive black hole corresponds to several years on Earth. Gravitational time dilation around black holes isn't just theoretical. It has practical implications for our understanding of the universe. It challenges our perception of time as a constant and reveals how gravity can fundamentally alter the flow of time itself. Now let's talk about spaghettification. The term spaghettification may sound humorous, but it describes a very real and terrifying process that occurs near black holes. It is also known as the tidal disruption effect. Spaghettification is what happens to objects that get too close to a black hole. Black holes generate immense tidal forces due to the steep gradient in gravitational strength between different points on an object. For example, if you were falling feet first toward a black hole, the gravitational pull on your feet would be significantly stronger than the pull on your head. This difference stretches your body lengthwise while simultaneously compressing it sideways, resulting in a noodle-like form. That's why it is called spaghettification. For smaller black holes, the tidal forces are so intense near the event horizon that spaghettification occurs well before you reach it. However, for supermassive black holes, the event horizon is farther out, and the tidal forces at this boundary are comparatively weaker. This means you could theoretically cross the event horizon of a supermassive black hole intact, at least temporarily, before experiencing spaghettification closer to the singularity. Objects that undergo spaghettification are often completely torn apart, with their individual atoms stretched and compressed. This process produces powerful bursts of X-rays and gamma rays, which astronomers can detect as signatures of material being consumed by black holes. Such catastrophic events provide valuable opportunities to study the physics of black holes and the extreme conditions near their event horizons. The concepts of time dilation and spaghettification underscore the strange and alien nature of black holes. They challenge our understanding of physics and highlight the extremes to which matter and spacetime can be pushed in the universe. Moving to our next topic, which is black hole and singularity. The concept of a singularity lies at the heart of what makes black holes some of the most mysterious and fascinating objects in the universe. Singularity is a point where the known laws of physics break down, where matter is compressed to infinite density, and where the fabric of spacetime itself becomes infinitely curved. It is a place where gravity becomes so overwhelming that our current understanding of the universe ceases to apply. To explore the singularity of a black hole is to venture into the unknown, where the rules of general relativity and quantum mechanics collide, and where the very nature of reality is called into question. The story of the singularity begins with the formation of a black hole. When a massive star exhausts its nuclear fuel, it can no longer support itself against the crushing force of its own gravity. The star collapses inward, and if its core is sufficiently massive, this collapse continues unchecked. The matter is compressed into an increasingly smaller volume, and the gravitational field grows stronger and stronger. Eventually, the star's core reaches a point where the density becomes infinite, and spacetime curvature becomes infinite as well. This is the birth of a singularity, hidden deep within the black hole, shrouded by the event horizon, the boundary beyond which nothing, not even light, can escape. The singularity is a place of extremes. According to general relativity, the equations that describe gravity and spacetime, the singularity is a point of zero volume and infinite density. All the mass of the collapsed star is concentrated at this single point, creating a gravitational pull so intense that it warps the very fabric of the universe. Time and space cease to exist at the singularity. For an outside observer, time appears to slow down near the event horizon, coming to a complete stop at the horizon itself. But for someone unfortunate enough to fall into a black hole, time would continue to flow, leading them inexorably toward the singularity. Once they cross the event horizon, there is no turning back. The singularity becomes their inevitable destination. What happens at the singularity is one of the greatest mysteries in physics. General relativity predicts that the gravitational forces become infinite, tearing apart anything that approaches it. This process is often referred to as spaghettification, where the tidal forces stretch and compress objects into long, thin strands. But the singularity itself is a place where the laws of physics as we know them fail. Infinite density and infinite curvature are not physical concepts that can be easily reconciled with our understanding of the universe. They are mathematical predictions that signal the limitations of general relativity, suggesting that a more complete theory, It unifies gravity with quantum mechanics. It is needed to describe what truly happens at the center of a black hole. The singularity is also intimately connected to the concept of spacetime. In the framework of general relativity, spacetime is a dynamic entity that can be curved and warped by mass and energy. Near a black hole, spacetime is so severely curved that it forms a kind of funnel, with the singularity at its bottom. This curvature is so extreme that it creates a one-way path. Anything that enters the black hole is destined to reach the singularity. The singularity is not just a point in space, but a moment in time. It is a future that cannot be avoided once the event horizon is crossed. One of the most intriguing aspects of the singularity is its relationship with time. In the context of a black hole, the singularity represents the end of time. For an object falling into a black hole, time progresses normally until it reaches the singularity, where it effectively ends. This is not just a philosophical idea, but a mathematical consequence of the equations of general relativity. The singularity is a boundary beyond which spacetime itself cannot be extended. It is a place where the universe comes to an end. The existence of singularities raises profound questions about the nature of reality. Are singularities real physical entities? Or are they merely artifacts of our incomplete theories? Some physicists believe that singularities are not truly infinite, but are instead a sign that general relativity breaks down under extreme conditions. They argue that quantum effects, which are not accounted for in classical general relativity, might prevent the formation of a true singularity. For example, in quantum gravity theories like string theory or loop quantum gravity, the extreme conditions near the center of a black hole might give rise to new phenomena that replace the singularity with something else, perhaps a quantum foam or a bridge to another region of spacetime. The singularity also plays a central role in the black hole information paradox, one of the most significant unsolved problems in theoretical physics. If information about the matter that falls into a black hole is lost at the singularity, it would violate the principles of quantum mechanics, which dictate that information must always be preserved. Resolving this paradox may require a deeper understanding of the singularity and its role in the universe. In the end, the singularity of a black hole is a place of mystery and wonder, a frontier where our understanding of the universe is pushed to its limits. It challenges us to rethink our assumptions about space, time, and the fundamental laws of physics. While we may never directly observe a singularity, the quest to understand it drives some of the most exciting research in modern physics. Whether it is through the development of a theory of quantum gravity, the study of Hawking radiation, or the exploration of alternative models of black holes, the singularity remains a beacon, guiding us toward a deeper understanding of the cosmos. It is a reminder that, even in the darkest corners of the universe, there is always more to discover. Moving to our next topic, which is quasi-periodic oscillations, a clue to black hole masses. Black holes, some of the most mysterious and fascinating objects in the universe, reveal themselves in a variety of ways. One of the key methods scientists use to study them is by observing the X-ray emissions from their accretion disks, the swirling disks of gas and dust that form around black holes as they pull in matter. Sometimes, these X-ray emissions flicker at specific frequencies, a phenomenon known as quasi-periodic oscillations, QPOs. These flickers are thought to be caused by material moving along the inner edge of the accretion disk, near the innermost stable circular orbit, the closest point to the black hole where matter can still orbit stably. Because the frequency of these oscillations is linked to the mass of the black hole, QPOs provide a powerful tool for estimating the mass of black hole candidates, offering an alternative to other measurement methods. While QPOs help us understand stellar mass black holes, the story of supermassive black holes unfolds on a much grander scale. At the heart of many galaxies, including our own Milky Way, lies a supermassive black hole. These colossal objects, millions or even billions of times more massive than the Sun, are often found in active galactic nuclei AGN, regions at the centers of galaxies that emit enormous amounts of energy. AGN are some of the brightest objects in the universe, and their power is thought to come from the supermassive black holes at their cores. The standard model of an AGN includes three main components: a supermassive black hole, an accretion disk of gas and dust swirling around it, and two jets of particles shooting out from the black hole's poles at nearly the speed of light. Although supermassive black holes are believed to exist in most galaxies, only a few have been studied in enough detail to confirm their presence and measure their masses. Some of the most notable examples include the Andromeda Galaxy. It is our closest galactic neighbor, M87, which hosts one of the largest known supermassive black holes. Another fascinating case is OJ-287, a galaxy that contains a pair of supermassive black holes orbiting each other. These discoveries have led scientists to conclude that nearly every galaxy contains a supermassive black hole at its center. This idea is supported by the M-sigma relation, a strong correlation between the mass of a galaxy's supermassive black hole and the velocity dispersion of stars in the galaxy's bulge. This relationship suggests that the formation of supermassive black holes is closely tied to the formation of galaxies themselves. But how do scientists detect black holes that aren't actively feeding or surrounded by bright accretion disks? One method is through gravitational lensing, a phenomenon where the immense gravity of a black hole bends and distorts the light from objects behind it. There are two main types of gravitational lensing. The first one is weak lensing, which causes slight distortions or shifts in the position of background objects. The other one is microlensing, which occurs when the lensing object is small and the background object is unresolved. In microlensing, the black hole temporarily brightens the light from a distant star as it passes in front of it. This technique has been used to detect black holes that would otherwise remain hidden. In the early 2000s, astronomers reported the first candidate detections of black holes using microlensing, and in January 2022, they confirmed the first detection of an isolated black hole through this method. This was a major milestone, as isolated black holes are much harder to detect than those in binary systems or at the centers of galaxies. Another way to observe the effects of a black hole's gravity is by studying stars that orbit it. For example, stars orbiting Sagittarius could provide valuable insights into the black hole's properties. As these stars move through the black hole's intense gravitational field, their light can be bent and magnified, creating subtle but detectable lensing effects. These observations not only help scientists measure the black hole's mass, but also test the predictions of general relativity in extreme environments. From the flickering X-rays of accretion disks to the powerful jets of active galactic nuclei, black holes reveal themselves in many ways. Quasi-periodic oscillations help us estimate their masses, while the study of galactic nuclei and gravitational lensing provides clues about their role in the universe. Whether through the subtle distortions of microlensing or the dramatic flares of AGN, black holes continue to captivate scientists and challenge our understanding of the cosmos. Each discovery brings us closer to unraveling the mysteries of these enigmatic objects and their profound influence on the universe. Now let's talk about black holes' growth and evaporation. Once a black hole has formed, it can continue to grow by absorbing additional matter. Any black hole will absorb gas and interstellar dust from its surroundings. This growth process is one possible way through which some supermassive black holes may have been formed. Although the formation of supermassive black holes is still an open field of research. A similar process has been suggested for the formation of intermediate mass black holes found in globular clusters. Black holes can also merge with other objects such as stars or even other black holes. This is thought to have been important, especially in the early growth of supermassive black holes, which could have formed from the aggregation of many smaller objects. The process has also been proposed as the origin of some intermediate mass black holes. In 1974, Stephen Hawking made a groundbreaking prediction. He discovered black holes aren't completely black. Instead, they emit tiny amounts of radiation, now called Hawking radiation. This happens because of quantum effects near the edge of a black hole. It is known as the event horizon. Hawking showed that black holes should emit particles that behave like a perfect black body, which is something that emits thermal radiation based on its temperature. This discovery was a big deal because it combined ideas from quantum mechanics and general relativity. These are two fundamental theories in physics. The temperature of this radiation depends on the black hole's size. Smaller black holes are hotter and emit more radiation, while larger black holes are colder and emit less. For example, a black hole with the mass of our Sun, which is 1 solar mass, would have a Hawking temperature of just 62 nanokelvins. That is 62 billionths of a degree. This is much colder than the cosmic microwave background, which is the leftover heat from the Big Bang and has a temperature of about 2.7 Kelvin. Because of this, most black holes in the universe actually absorb more energy from the CMB than they emit through Hawking radiation. So they grow in size over time instead of shrinking. However, if a black hole is very small, let's say less massive than the Moon, its Hawking temperature would be higher than the CMB. This means it would lose more energy than it gains and eventually evaporate. But don't worry, black holes like this aren't common in the universe. They would have to be primordial black holes, which are hypothetical black holes that could have formed in the early universe. Now let's talk about really tiny black holes. Imagine a black hole with the mass of a car. It would be incredibly small. It would be way smaller than an atom. It would evaporate in just a nanosecond. During its final moments, it would release a huge burst of energy, shining brighter than 200 suns. Even smaller black holes, like one with the mass of a particle, would evaporate almost instantly, less than a fraction of a second. At such small scales, the rules of quantum gravity might come into play, but scientists aren't sure yet if this would stabilize the black hole or change how it evaporates. Detecting Hawking radiation from black holes is incredibly hard because it's so weak. For most black holes, the radiation is drowned out by other sources of energy in the universe. Since black holes don't emit light or other electromagnetic radiation except for Hawking radiation, scientists can't observe them directly. Instead, they look for indirect evidence. For example, they study how black holes affect their surroundings. A black hole's gravity can pull gas and dust, forming a glowing disk of material called an accretion disk. Sometimes, black holes also shoot out powerful jets of particles. By observing these effects, scientists can infer the presence of black holes and learn more about their properties. Moving to our next topic, which is detection of gravitational waves from merging black holes. On September of 2015, a monumental discovery shook the world of science. Laser Interferometer Gravitational Wave Observatory made the first ever direct detection of gravitational waves. These waves are ripples in the fabric of spacetime. It was predicted by Albert Einstein over a century ago in his theory of general relativity. For the first time, humanity had concrete evidence of these elusive waves, and the source was just as extraordinary. It was coming from the collision and merger of two black holes. The gravitational waves detected by LIGO came from a violent cosmic event involving two black holes. One was about 36 times the mass of the Sun, and the other was around 29 times the mass of the Sun. These massive objects had been orbiting each other, slowly spiraling closer and closer until they finally merged into a single black hole. The energy released in this collision sent ripples through spacetime, which traveled across the universe for over 1 billion years before reaching Earth. When the signal arrived, it matched almost perfectly with what scientists had predicted for such an event, confirming not only the existence of gravitational waves but also providing the most direct evidence yet for black holes. The signal itself was incredibly revealing. Before the merger, The two black holes were just 350 kilometers apart. It is an astonishingly small distance for objects so massive. This extreme closeness meant the objects had to be incredibly dense and compact. These characteristics that perfectly matched the description of black holes. It also captured the post-merger ringdown, a kind of echo produced as the newly formed black hole settled into a stable state. This ringdown is like a fingerprint of a black hole. The frequency reached Earth and faded quickly. It perfectly matched with the predictions from theoretical models and computer simulations. By analyzing this ringdown, scientists could determine the mass and spin of the final black hole. One of the most fascinating aspects of the signal was that it confirmed the presence of a photon sphere. It is a region around a black hole where gravity is so strong that light can orbit it. This is a key feature of black holes, and its detection provided strong evidence for their existence. However, the signal couldn't completely rule out the possibility of other exotic and ultra-dense objects that might also have a photon sphere. Still, black holes remain the most plausible explanation, and the discovery was a major step forward in our understanding of these mysterious objects. This groundbreaking observation was significant for several reasons. First, it provided the most concrete evidence yet for the existence of black holes, particularly stellar mass black holes, which form from the collapse of massive stars. Second, it was the first time scientists had observed a black hole binary. Here, binary means a pair of black holes orbiting each other. Third, the black holes involved were much heavier than expected, with masses over 25 times that of the Sun. This challenged some existing theories about how such massive black holes form and opened up new questions for researchers to explore. Since that first detection in 2015, LIGO and its partner observatory Virgo have detected many more gravitational wave events. These include additional black hole mergers, collisions between neutron stars known as the incredibly dense remnants of dead stars, and even possible mergers between a black hole and a neutron star. Each new detection provides fresh insights into the nature of black holes, neutron stars, and the universe itself. Gravitational wave astronomy has become a powerful tool for exploring the cosmos, allowing us to listen to events that are invisible to traditional telescopes and uncovering secrets about the most extreme objects in the universe. Now we are going to discuss about relation between relativity and black hole. In 1915, Albert Einstein developed his theory of general relativity. Before this development, he proved gravity does influence light's motion. Only a few months later, Carl found a solution to the Einstein field equations. It describes the gravitational field of a point mass and a spherical mass. A few months after Carl and a student of Hendrik Lorentz independently gave the same solution for the point mass and wrote more extensively about its properties. This solution had a peculiar behavior, which is now called the Carl radius, where it became singular. It means some of the terms in the Einstein equations became infinite. Einstein's theory allows us to rule out large densities for visible stars like Betelgeuse. This theory states that a star of 250 million kilometers radius could not possibly have so high a density as the Sun. Firstly, the force of gravitation would be so great that light would be unable to escape from it. Secondly, the red shift of the spectral lines would be so great that the spectrum would be shifted out of existence. Thirdly, the mass would produce so much curvature of the spacetime metric that space would close up around the star, which would leave us outside of the gravity. In 1939, Einstein attempted to prove that black holes were impossible in his publication. He used his theory of general relativity to defend his argument. Months later, Oppenheimer and his student Snyder provided a new model. It was called Oppenheimer-Snyder model. In their paper, they predicted the existence of black holes. They made no reference to Einstein's recent publication. Oppenheimer and Snyder used Einstein's own theory of general relativity to show the conditions on how a black hole could develop. Now we will discuss about entropy and thermodynamics of black holes. In 1971, Stephen Hawking made an interesting discovery about black holes. He found that the total surface area of black holes' event horizons never decreases, not even when black holes merge. This rule is now known as the second law of black hole mechanics. It's quite similar to the second law of thermodynamics. It states that the total entropy or disorder of an isolated system can never decrease. Normally, objects at absolute zero temperature have zero entropy, and scientists assumed the same for black holes. But this assumption created a problem. If black holes swallowed objects full of entropy without increasing their own, the total entropy of the universe would decrease, violating the second law of thermodynamics. To solve this, physicist Jacob proposed that black holes must have entropy, and their entropy should be proportional to their surface area. This idea linked black holes more closely to thermodynamics. The connection became even stronger in 1974, when Hawking discovered that black holes emit radiation. Now it is called Hawking radiation. This radiation is similar to the heat emitted by normal objects, meaning black holes have a temperature. But if black holes radiate energy, they lose mass and shrink over time. This seemed to contradict the second law of black hole mechanics. However, physicists showed that if we combine the entropy of everything outside the black hole with 1/4 of its surface area, then the total entropy always increases. This led to the first law of black hole mechanics, where the mass of the black hole acts like energy, surface gravity represents temperature, and area represents entropy. A strange thing about black hole entropy is that it scales with surface area rather than volume. Normally, entropy increases with the volume of a system, but for black holes, it's tied to their event horizon. This unusual property led scientists Gerard and Leonard to propose the holographic principle. This principle suggests that everything happening inside a region of space can be fully described by data on its boundary. In other words, the universe might function like a hologram, where three-dimensional reality is encoded on a two-dimensional surface. Although we can use general relativity to estimate black hole entropy, this is not a complete answer. In normal physics, entropy is understood by counting all the microscopic states a system can have. Without a full theory of quantum gravity, scientists couldn't properly calculate black hole entropy this way. However, progress has been made. In 1995, Andrew Strominger and Kamran Vafa used string theory to count the microscopic states of a particular type of black hole. Their result matched Bekenstein and Hawking's equation, providing strong support for the idea that black hole entropy has a deep quantum explanation. Since then, similar calculations have been done in other approaches to quantum gravity, including loop quantum gravity. Now let's talk about some other theories that are related to black hole. While the classical concept of black holes has been extensively studied, alternative theories challenge and expand our understanding of these enigmatic objects. Among these, there are fuzzballs and gravastars, which offer radically different perspectives on the nature of black holes. The idea of fuzzball theory was originated from string theory. Fuzzball's theory suggests that black holes are not singularities surrounded by event horizons, but rather massive fuzzy objects composed of tangled strings and brains. Unlike classical black holes, fuzzballs do not have a point of infinite density. Instead, they represent a finite structure that resolves many paradoxes associated with black holes, such as the information loss problem. In this framework, the event horizon is replaced by a surface where the strings are densely packed, preventing the complete collapse into a singularity. The fuzzball concept challenges traditional ideas about the nature of spacetime and offers a potential bridge between general relativity and quantum mechanics. However, it remains a theoretical construct, requiring more evidence and exploration to validate its predictions. The second theory is about gravastars. Gravastars, or gravitational vacuum stars, are another exotic alternative to black holes. Instead of a singularity, a gravastar is thought to contain a core of exotic matter surrounded by a thin shell of energy. This structure creates a gravitational field similar to of a black hole, but without an event horizon. Gravastars challenge the black hole paradigm by suggesting that what we observe as a black hole might actually be a different type of compact object. Unlike black holes, gravastars would not trap information or matter forever, offering a solution to some of the paradoxes associated with event horizons and singularities. These alternative theories highlight the ongoing efforts to reconcile the mysteries of black holes. It uses the principles of quantum mechanics and general relativity. As our observational capabilities improve, we may one day determine whether these exotic objects exist in the universe, or whether they remain purely theoretical constructs. Black holes, whether through their growth, interactions, or the theories surrounding them, continue to be a cornerstone of modern astrophysics. Their study not only deepens our understanding of the cosmos, but also challenges us to rethink the very nature of reality. Now we will discuss properties and structure of black holes. Black holes are unique because they have only three defining features: mass, charge, and spin. This idea is known as the no-hair theorem, which suggests that black holes are incredibly simple despite their mysterious nature. If two black holes share the same mass, charge, and spin, they are indistinguishable, no matter how they were formed. These properties can be measured from a distance. A black hole's mass affects its gravitational pull, charge influences how it interacts with other charged particles, and spin creates a frame-dragging effect, twisting spacetime around it. When an object falls into a black hole, all information about its original form is spread out and lost to outside observers. Scientists compare the black hole's event horizon to a stretchy conductive membrane with resistance. Unlike normal physical systems, where time can be reversed, black holes do not allow information to escape, leading to the information loss paradox. Now let's talk about types of black hole. The simplest type of black hole is one that has mass but neither electric charge nor spin. These are called Schwarzschild black holes, named after Karl Schwarzschild, who discovered their solution in 1916. According to a principle called Birkhoff's theorem, these black holes are perfectly spherical, and their gravitational field is identical to that of any other spherical object with the same mass. This means that from a distance, a black hole's gravity behaves just like a normal star or planet of equal mass. The common idea that black holes suck in everything is only true near their event horizon. Far away, their pull is just like any other massive body. There are also more complex type of black holes. If a black hole carries an electric charge, it is described by the Reissner metric. If it rotates, it follows the Kerr metric. The most general type, which has both charge and rotation, is described by the Kerr metric. While black holes can have any mass above a certain threshold, their charge and spin are limited by the laws of physics. Moving to our next topic, which is formation and evolution of black holes. For a long time, scientists debated whether black holes could actually form in nature. Even Albert Einstein initially believed they wouldn't. He thought that as a star collapsed, its rotation would prevent it from shrinking into a singularity. However, by the late 1960s, most physicists were convinced that black holes were real and could form when massive stars collapsed. Once an event horizon forms, general relativity predicts that a singularity will inevitably appear inside. British physicist Roger Penrose proved this mathematically, while Stephen Hawking later showed that similar singularities existed in models of the Big Bang. The study of black holes became more mainstream when researchers realized that their properties were surprisingly simple and followed clear laws, much like thermodynamics. Gravitational collapse plays a vital role in the formation of black holes. Black holes form when an object collapses under its own gravity. In stars, this happens when they run out of fuel and can no longer generate enough pressure to resist gravitational collapse. Sometimes, a star might receive extra mass from another source, pushing it beyond a critical limit and causing collapse. If the collapsing object is not too massive, it may stop at an intermediate stage. Then it will form a neutron star or another type of dense object. However, if its mass exceeds about 3 to 4 times that of the Sun, no known force can stop the collapse. It will lead to the formation of a black hole. Massive stars in the early universe could have formed black holes up to 1,000 times the mass of the Sun. These could have acted as the seeds of the supermassive black holes, found at the centers of galaxies today. Some theories suggest that enormous black holes, around 100,000 times the Sun's mass, could have formed directly from collapsing gas clouds in the young universe. Interestingly, while most energy from a collapsing star is emitted quickly, an external observer never actually sees the formation of the black hole. Due to gravitational time dilation, light from the collapsing star takes longer to reach an observer. The final light emitted just before the event horizon forms would take an infinite amount of time to be seen, meaning the collapsing star seems to freeze and fade away rather than fully disappear. Now we will discuss primordial black holes and the Big Bang. In today's universe, high-density regions where black holes can form only exist inside stars. But in the early universe, shortly after the Big Bang, the universe was much denser. If there were even small density fluctuations, some regions could have collapsed into primordial black holes. The sizes of these black holes could have varied widely, from tiny ones with the mass of an asteroid to enormous ones as massive as a galaxy. However, despite the early universe being incredibly dense, it didn't collapse into a giant black hole. This is because the universe was expanding too quickly for gravity to pull everything together. The rapid expansion during the Big Bang helped prevent a universal collapse. Although no primordial black holes have been confirmed yet, scientists are still searching for evidence of their existence. If they are found, they could provide valuable insights into the early universe and the nature of gravity itself. High-energy collisions are another theoretical way black holes could form. If an event reaches an extreme density, it could create a black hole. However, no such black holes have been observed in experiments, either directly or through missing mass in particle accelerator collisions. This suggests that there is a lower mass limit for black holes, where quantum effects render classical general relativity predictions are invalid. This would mean that no high-energy process on or near Earth could create black holes. However, some quantum gravity models, such as certain brane-world scenarios, suggest that the minimum black hole mass could be much lower. If these theories hold true, micro-black holes could form in high-energy collisions, such as those occurring when cosmic rays hit Earth's atmosphere, or inside the Large Hadron Collider at CERN. Despite these possibilities, most experts consider the formation of black holes in such conditions highly unlikely. Even if micro-black holes did form, they would evaporate almost instantly within a fraction of a second, making them harmless to Earth. Now let's discuss photon sphere and ergosphere. The photon sphere is a region where light can orbit a black hole. It is found in a non-rotating black hole. Unlike the event horizon, light can escape from the photon sphere, but its orbits are unstable. A slight disturbance will either send the photon outward into space or cause it to spiral into the black hole. For rotating black holes, the photon sphere's location depends on the black hole's spin and the direction in which the photon moves. The next one is egrosphere. Rotating black holes are surrounded by a special region called the ergosphere. Here, spacetime itself is dragged along with the black hole spin. The effect is known as frame dragging. Any object within the ergosphere is forced to move in the direction of the black hole's rotation. To remain stationary, it would have to move faster than the speed of light, which is impossible. The ergosphere extends outwards from the event horizon, touching it at the poles but expanding further at the equator. Unlike the event horizon, objects can escape from the ergosphere. This leads to an interesting process known as the Penrose process, where objects can gain energy from the black hole's rotation, causing the black hole to spin more slowly. This mechanism, along with strong magnetic fields, explain the immense energy output of quasars and other powerful cosmic phenomena. Now moving to the next topic, which is black holes in astrophysics. Black holes are not static entities. They are dynamic systems that evolve, interact, and even challenge our understanding of astrophysics. Their interactions with companion stars and the development of exotic theories surrounding their nature have opened new frontiers in our quest to understand the universe. In recent years, science has discovered how black holes grow through accretion and mergers. Accretion occurs when a black hole pulls in matter from its surroundings, such as gas, dust, or even stars. This material forms an accretion disk. It is a swirling ring of high-energy particles that heats up to millions of degrees as it spirals inward. The intense heat and energy produced by this process often make accreting black holes some of the brightest objects in the universe. It emits X-rays and other high-energy radiation. Supermassive black holes, found at the centers of galaxies, grow over billions of years by accreting vast amounts of material. In contrast, stellar mass black holes, which form from the remnants of massive stars, grow on shorter timescales, limited by the availability of nearby matter. Mergers are another significant growth mechanism of supermassive black holes. When two black holes collide, they combine to form a larger black hole, releasing energy in the form of gravitational waves. These ripples in spacetime, first detected by the LIGO and Virgo observatories, provide direct evidence of black hole mergers. Over cosmic time, such collisions play a crucial role in the growth of supermassive black holes, particularly in densely populated regions like galaxy cores. The timescales for black hole growth depends on few factors. Stellar mass black holes can accumulate mass relatively quickly if they are in a dense environment. However, supermassive black holes require billions of years to reach their enormous sizes, often through a combination of accretion and repeated mergers. When black holes exist in binary systems, it is paired with a companion star. Their interactions become even more fascinating. The black hole's intense gravitational pull can strip material from the companion star, forming an accretion disk around the black hole. This process releases vast amounts of energy, often detectable as X-rays. Systems like these are called X-ray binaries, and they are one of the primary ways astronomers identify black holes in the universe. The interaction between a black hole and its companion star is not only violent, but also incredibly dynamic. As material from the star flows toward the black hole, it undergoes heating and compression, creating bursts of radiation that can vary over time. Observing these fluctuations helps scientists understand the black hole's properties, such as its mass and spin. In some cases, black holes in binary systems also eject powerful jets of plasma at nearly the speed of light. These jets are thought to be driven by the rotation of the black hole and the magnetic fields within the accretion disk. The study of such jets provides insights into the physics of relativistic plasmas and the mechanisms by which black holes transfer energy to their surroundings. Moving to our next topic. Now let's talk about possibility of harnessing black holes. Black holes, with their immense gravitational pull and seemingly limitless energy, spark fascinating discussions about whether humanity could ever harness their power. While this remains firmly in the realm of speculation and advanced theoretical physics, the concept is not without merit. If future civilizations develop the technology to approach black holes safely, they could tap into them as the ultimate energy sources. One of the most well-known ideas for extracting energy from black holes is the Penrose process, named after physicist Roger Penrose. This process involves utilizing the ergosphere of a rotating black hole. It is a region just outside the event horizon, where spacetime itself is dragged by the black hole's spin. In theory, an object entering the ergosphere could split into two, with one part falling into the black hole and the other escaping. The escaping piece would gain energy, which could then be harvested. This method relies on the black hole's rotation, effectively converting some of its angular momentum into usable energy. Another speculative concept involves constructing a Dyson sphere around a black hole. A Dyson sphere is a hypothetical megastructure designed to capture a star's energy by enclosing it. In the case of black holes, this structure would surround the accretion disk, where infalling matter is heated to extreme temperatures and emits vast amounts of radiation. The radiation could be captured and converted into usable energy. This approach would take advantage of the incredible energy output of the accretion process, which can sometimes outshine entire galaxies. Theoretical physicists have also explored the idea of using Hawking radiation. It was predicted by Stephen Hawking. He proved that black holes slowly emit energy and lose mass over time. While the radiation is incredibly faint for black holes of stellar or supermassive sizes, a sufficiently small black hole could emit significant amounts of energy, potentially making it a compact and efficient power source. In theory, humans could even create miniature black holes and control their energy output, though this concept remains highly speculative and raises profound technical and ethical questions. Now we are going to talk about ethical and technical challenges of harnessing black holes. Harnessing the energy of black holes would not be easy at this moment. Technologically, approaching a black hole safely would require materials and systems far beyond what humanity currently possesses. The immense gravitational forces and intense radiation would destroy any known spacecraft long before it could get close enough. Moreover, maintaining control over such a powerful energy source could pose catastrophic risks. An error in the system might unleash destructive forces on an unimaginable scale. Ethically, the use of black holes raises profound questions. Should humanity interfere with such extreme cosmic phenomena? Could we disrupt the natural processes of galaxies or endanger other civilizations? The sheer scale and power of black holes demand a level of responsibility and foresight that might exceed humanity's current capacity for ethical decision-making. Now let's talk about what have we observed in this decade. The Event Horizon Telescope, EHT, is a groundbreaking project designed to take pictures of black holes. It specifically focuses on their event horizons. It is the point of no return where nothing, not even light, can escape. One of its main targets is the supermassive black hole. It is located at the center of our own galaxy, the Milky Way. It is called Sagittarius A, but the EHT didn't stop there. It also observed the supermassive black hole at the heart of another galaxy, Messier 87. It is called M87. In April 2017, the EHT team used a network of 8 radio telescopes spread across 6 mountains and 4 continents to observe M87's black hole. These telescopes worked together like a giant Earth-sized telescope, collecting data over 10 days. After 2 years of processing this massive amount of data, the EHT team made history in April 2019 by releasing the first ever direct image of a black hole. The image wasn't of the black hole itself. Since black holes don't emit light, they appear completely black. Instead, the image showed the glowing hot gas swirling around the event horizon. This gas, heated to billions of degrees, forms a bright ring of light around the black hole's shadow. In the EHT image, this ring appeared in shades of orange and red, making the black hole visible for the first time. Now let's talk about imaging Sagittarius A, or the Milky Way's black hole. On May 12, 2022, the EHT team released another historic image. This time it was the image of Sagittarius A, the supermassive black hole at the center of our galaxy. While it looks similar to the M87 black hole, with a ring-like structure and a dark shadow in the middle, Sagittarius A was much harder to image. Why? Because it's over 1,000 times smaller and less massive than M87's black hole, and its surroundings are much more chaotic. The gas and plasma around Sagittarius A move and change rapidly, making it harder to get a clear picture. Additionally, the turbulent plasma between Earth and the galactic center blurred parts of the image, especially at longer wavelengths. Despite these challenges, the EHT team succeeded, revealing a ring of light around Sagittarius A that matches predictions from Einstein's theory of general relativity. This ring is created by light bending around the black hole's immense gravity, a phenomenon called gravitational lensing. Now let's discuss what the images tell us. The EHT images aren't just pretty pictures. They're packed with scientific information. For example, the brightening of the ring in the bottom half of the M87 image is caused by a phenomenon called Doppler beaming. This happens because the gas around the black hole is spinning at nearly the speed of light. When the gas moves toward us, it appears brighter. When it moves away, it appears dimmer. This tells us that the black hole's accretion disk is rotating clockwise, and we're seeing it almost edge-on. Interestingly, the ring of light in the EHT images isn't just from the side of the disk facing us. Because of the black hole's extreme gravity, light from the far side of the disk bends around the black hole and reaches us too. This means we're seeing the entire disk, even the part that's technically behind the black hole. It's like the black hole's gravity is acting as a giant cosmic mirror. Now let's talk about magnetic fields and jets. In 2015, the EHT team made another exciting discovery. They detected magnetic fields just outside the event horizon of Sagittarius A. These magnetic fields are a mix of orderly and tangled lines, and they play a key role in shaping the black hole's environment. Theoretical models had predicted their existence, but this was the first time they were observed directly. In April 2023, the EHT team took things a step further. They released an image showing not only the shadow of the M87 black hole, but also its high-energy jet. It is a powerful beam of particles shooting out from near the black hole at nearly the speed of light. This was the first time both the black hole's shadow and its jet were seen together, giving scientists a more complete picture of how black holes interact with their surroundings. We have discussed EHT significantly, but why EHT matters? The EHT's work is revolutionary because it allows us to see black holes in a way that was once thought impossible. By combining data from telescopes around the world, the EHT acts like a giant magnifying glass, revealing details about the most mysterious objects in the universe. These images confirm predictions made by Einstein's theory of general relativity and help us understand how black holes grow, how they affect their surroundings, and how they launch jets of particles that can travel across entire galaxies. Moving to our next topic, which is black holes' impact across philosophy, literature, and media. Black holes are the subject of astrophysics, resonate far beyond the boundaries of science. Their mysteries inspired philosophical thought, literature, and visual storytelling. These cosmic enigmas invite reflection on humanity's place in the universe, bridging the gap between science and the humanities. Black holes challenge our perceptions of reality and evoke some of the most profound philosophical questions. As symbols of mystery, they embody the human struggle to comprehend the incomprehensible. The existence of a singularity, where space-time curvature becomes infinite and the laws of physics cease to function, pushes us to confront the limits of human understanding. Can we ever fully grasp what lies beyond the event horizon, or will it remain forever hidden, a boundary of knowledge we cannot cross? The concept of infinity plays a central role in the philosophical implications of black holes. Singularities represent infinite density in a finite region of space, a paradox that defies conventional reasoning. This raises questions about the nature of infinity itself. Is it a physical reality or merely a construct of human thought? Philosophers and scientists alike grapple with the implications of such paradoxes, which blur the line between mathematics, physics, and metaphysics. Black holes also invite reflection on the nature of time. Near a black hole, time slows down due to its immense gravitational field, a phenomenon known as time dilation. For an observer falling into a black hole, time would stretch infinitely as they approached the event horizon. This challenges our linear understanding of time and raises profound questions. Is time an absolute property of the universe, or is it subjective, shaped by the fabric of spacetime? Such reflections extend beyond physics, delving into the philosophical exploration of existence itself. Black holes also inspire science fiction and art. The mystery of black holes have made them a powerful source of inspiration for writers, filmmakers, and artists. These cosmic phenomena are more than scientific curiosities. They are narrative devices that explore themes of survival, exploration, and the limits of human knowledge. In science fiction, black holes often serve as portals to other dimensions, gateways to the unknown, or obstacles for daring space travelers. They symbolize the allure and danger of venturing into uncharted territories, echoing humanity's eternal quest to explore the unknown. Novels like Event Horizon and The Black Hole War explore the scientific and existential questions surrounding these enigmatic objects, blending hard science with imaginative speculation. Artists have been captivated by black holes, using them as metaphors for mystery and transformation. Abstract depictions of black holes, swirling masses of light and darkness, convey the awe-inspiring power and beauty of these celestial objects. In visual art, black holes often evoke feelings of wonder, fear, and the sublime, reflecting the complex emotions they inspire. One of the most iconic portrayals of black holes in popular media is Christopher Nolan's Interstellar. The film brought black holes into the cultural spotlight, combining scientific accuracy with breathtaking visuals. The depiction of the black hole was based on calculations by renowned physicist Kip Thorne, ensuring that its appearance adhered to the principles of general relativity. In Interstellar, the black hole serves as both a narrative and symbolic centerpiece. It represents humanity's desperation to find a new home and the sacrifices required for exploration. The film's exploration of time dilation near black hole provided visceral understanding of this complex phenomenon. The success of Interstellar highlights the power of storytelling in making scientific concepts accessible to the public. It also demonstrates the interdisciplinary nature of black hole studies, where science, art, and philosophy intersect to create compelling narratives that inspire and educate. Black holes are more than astrophysical phenomena. They are symbols of humanity's quest to understand the universe and its mysteries. They challenge us to confront the unknown, bridging the divide between science and the humanities. By inspiring philosophical reflection, exploration, and cinematic innovation, black holes continue to captivate and enrich our understanding of the cosmos. Moving forward to our next topic, which is physics of black hole. Black holes are nature's most extreme laboratories, where the rules of physics are pushed to their absolute limits. Their immense gravitational forces and mysterious interiors make them one of the most fascinating topics in modern science. From the violent tidal forces near their event horizons to the potential discoveries from future space missions, black holes continue to test and expand our understanding of the universe. Tidal forces near black holes is called spaghettification. The intense gravitational field of a black hole creates one of the most extreme phenomena in the universe. This occurs when an object or a person gets stretched into a long and thin shape due to the differential gravitational forces acting on it. The gravitational pull at the object's closest point to the black hole is significantly stronger than the pull at its farthest point. This immense tidal force elongates the object into a spaghetti-like strand. That's why it is called spaghettification. For example, if a spacecraft ventured too close to a stellar mass black hole, it would experience such extreme tidal forces that it would be torn apart long before crossing the event horizon. Near supermassive black holes, the tidal forces are less intense at the event horizon. It means objects might theoretically survive longer before spaghettification occurs. Scientists use computer simulations to model how various objects behave as they fall into black holes. It offers a glimpse into these extreme environments. These simulations provide insights into how black holes consume matter and how the accretion of material forms the luminous disks we observe around them. The ultimate mystery remains inside the event horizon. The event horizon is the boundary of a black hole, beyond which nothing, not even light, can escape. What happens inside this mysterious boundary remains one of the greatest unanswered questions in physics. According to general relativity, anything crossing the event horizon is inevitably drawn toward the singularity, a point of infinite density where the curvature of spacetime becomes infinite. However, our current understanding of physics breaks down under such extreme conditions. Theoretical physicists speculate about what might lie beyond the event horizon. Some suggest that the singularity could be a gateway to another universe, while others argue that quantum effects might prevent the formation of a true singularity. The concept of a quantum black hole combines principles of quantum mechanics and general relativity. It is a potential framework for understanding what happens inside these enigmatic objects. One of the most tantalizing questions is whether we will ever know what lies beyond the event horizon. Since no information can escape from it, it seems impossible to directly observe the interior. However, advancements in theoretical physics, such as string theory and quantum gravity, might eventually provide indirect insights. Black holes continue to challenge the limits of human understanding, serving as a cosmic reminder of the mysteries that remain unsolved. Now let's discuss about unanswered questions in physics of black hole. While observations are set to revolutionize our understanding of black holes, many fundamental questions remain unanswered. These mysteries highlight the gaps in our knowledge and provide a roadmap for future research. One of the most intriguing questions in modern astrophysics is the relationship between dark matter and black holes. Dark matter, which makes up approximately 27% of the universe, remains undetected except through its gravitational effects. Some theories suggest that black holes could act as laboratories for studying dark matter. For instance, certain types of dark matter particles might interact with black holes in unique ways, leaving detectable signatures in their behavior. The observation of unusual patterns in the radiation emitted by accretion disks, or the detection of gravitational wave anomalies, could provide indirect evidence for dark matter. Moreover, some scientists have proposed that dark matter itself could consist of primordial black holes, small black holes formed shortly after the Big Bang. If this is true, it would reshape our understanding of both dark matter and the early universe. Confirming or disproving this hypothesis remains a key goal for future research. The next intriguing questions in modern astrophysics is the relationship between primordial black holes and the Big Bang. Primordial black holes represent another significant area of inquiry. Unlike stellar black holes, which form from the collapse of massive stars, primordial black holes are thought to have formed in the chaotic conditions of the early universe. Their existence could provide crucial insights into the physics of the Big Bang and the conditions that prevailed during the universe's first moments. Detecting primordial black holes is a monumental challenge, as they would likely be much smaller and fainter than their stellar or supermassive counterparts. However, their presence could be inferred through gravitational lensing, where their mass bends the light of distant objects, or through their potential contribution to the cosmic microwave background. If primordial black holes are found, they could also help solve the mystery of the origin of supermassive black holes, offering a possible explanation for how these giants formed so early in the universe's history. The future of black hole research lies at the intersection of observational capabilities and theoretical advancements. Theoretical physicists are continually refining our understanding of black holes, from their quantum properties to their role in the larger cosmos. Concepts like Hawking radiation, black hole thermodynamics, and quantum gravity remain active areas of study, with the potential to revolutionize not only black hole physics but our understanding of the universe itself. Future observations by instruments like JWST, ELT, and LISA will provide the data needed to test these theories and answer some of the most profound questions about black holes. At the same time, these tools will undoubtedly raise new questions, driving the next generation of scientists to explore the universe's most mysterious phenomena. Now we will discuss the golden age in the research of black hole. The year 1958 marked a pivotal moment in the study of black holes, when David Finkelstein introduced the concept of the event horizon as a perfect unidirectional membrane. In his paper, Finkelstein described how causal influences could cross this boundary in only one direction. This work did not contradict the earlier findings of J. Robert Oppenheimer and Hartland Snyder. They had described the gravitational collapse of a massive star into a black hole, but it provided a more comprehensive framework for understanding the behavior of spacetime near such an object. Around the same time, Martin Kruskal had independently discovered a complete extension of the Schwarzschild solution, which was later encouraged to be published. These breakthroughs laid the groundwork for the golden age of general relativity, a period during which black holes transitioned from mathematical curiosities to mainstream subjects of scientific inquiry. The golden age of general relativity was further catalyzed by the discovery of pulsars in 1967 by Jocelyn Bell Burnell. Initially, the nature of these rapidly rotating neutron stars was a mystery, but by 1969, it was established that they were the remnants of massive stars that had undergone gravitational collapse. This discovery not only confirmed the existence of neutron stars, but also reignited interest in other compact objects, such as black holes. It had previously been regarded as purely theoretical constructs. The realization that such extreme objects could exist in nature inspired researchers to discover properties and behavior of black holes. During this period, significant progress was made in solving the equations of general relativity to describe black holes. In 1963, Roy Kerr found an exact solution for a rotating black hole, a monumental achievement that provided a more realistic model of black holes in the universe. Since the most astrophysical objects are expected to have some degree of rotation. 2 years later, Ezra Newman extended Kerr's solution to include electric charge, which describes a black hole is continuously rotating and being charged. These solutions revealed the rich and complex structure of black holes, challenging earlier assumptions that they were simple and static objects. The work of Werner Israel and David Robinson further advanced the understanding of black holes by leading to the formulation of the no-hair theorem. This theorem states that a stationary black hole is fully characterized by just 3 parameters: mass, angular momentum, and electric charge. All other information about the matter that formed the black hole or fell into it is lost, encapsulated in these 3 quantities. This elegant result suggested that black holes are remarkably simple objects, despite their extreme nature. However, the existence of singularities within black holes remained a contentious issue. Initially, some physicists argued that singularities were artifacts of the highly symmetric conditions assumed in theoretical models and would not appear in more generic, realistic scenarios. This view was challenged in the late 1960s by Roger Penrose and Stephen Hawking, who used global techniques to prove that singularities are a generic feature of gravitational collapse. Their work demonstrated that singularities are an inevitable consequence of general relativity under a wide range of conditions, fundamentally altering the understanding of black holes. For this groundbreaking contribution, Penrose was awarded half of the 2020 Nobel Prize in Physics, with Hawking being ineligible due to his passing in 2018. The 1970s was the golden time in the science community. Scientists witnessed further breakthroughs in black hole physics, particularly with the identification of Cygnus X1, since it is the first widely accepted black hole candidate. Observations of this galactic X-ray source discovered in 1964 provided strong evidence for the existence of black holes in the universe. Around the same time, James Bardeen and Hawking developed the laws of black hole thermodynamics, drawing a striking analogy between the behavior of black holes and the laws of thermodynamics. These laws related the mass of a black hole to energy, its surface area to entropy, and its surface gravity to temperature, suggesting a deep connection between gravity, thermodynamics, and quantum mechanics. The analogy was completed in 1974 when Hawking made one of the most profound discoveries in theoretical physics. Black holes are not entirely black. Using quantum field theory in curved spacetime, Hawking showed that black holes emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. This radiation has a thermal spectrum, implying that black holes have a temperature and can lose mass over time, eventually evaporating completely. Hawking's discovery not only resolved a long-standing paradox about the fate of information in black holes, but also opened up new avenues for exploring the interplay between quantum mechanics and general relativity. The study of black holes has since become a cornerstone of modern physics, offering insights into the nature of space-time, gravity, and the fundamental laws of the universe. From Finkelstein's unidirectional membrane to Hawking's quantum radiation, the journey to understand black holes has been marked by groundbreaking discoveries and profound theoretical advances. Today, black holes continue to captivate scientists and the public alike, serving as cosmic laboratories for testing the limits of our knowledge and exploring the deepest mysteries of the cosmos. Moving to our next topic, which is Future Research Map of Black Hole. The study of black holes has rapidly advanced in recent years, but there remains a wealth of knowledge yet to uncover. As technology progresses, future research initiatives and cutting-edge observational tools will allow scientists to probe deeper into the mysteries of these enigmatic cosmic phenomena. From next-generation telescopes to unresolved questions in fundamental physics, the journey to understand black holes is far from complete. The ongoing exploration of black holes will rely heavily on advancements in observational technology. One of the most promising instruments in this effort is the James Webb Space Telescope. While the telescope is renowned for its ability to peer into the distant past and study the formation of stars and galaxies, it also holds potential for studying black holes. JWST's infrared capabilities allow it to observe the accretion disks of supermassive black holes with unparalleled clarity, even in the dusty environments of galactic cores. This will provide insights into how black holes interact with their host galaxies, how they grow over time, and the role they play in shaping the cosmos. Additionally, future observatories like the Extremely Large Telescope and the 30-meter telescope will contribute to black hole research. These ground-based telescopes, equipped with advanced adaptive optics, will offer unprecedented resolution and sensitivity. It will enable astronomers to study the dynamics of stars near black holes and detect smaller black holes within our galaxy. Another breakthrough tool in the study of black holes is the next generation of gravitational wave detectors. Instruments like Laser Interferometer Space Antenna and upgraded versions of Laser Interferometer Gravitational Wave Observatory will open new windows into the universe by detecting gravitational waves from merging black holes with even greater precision. Unlike electromagnetic observations, gravitational waves carry information about black holes that is unaffected by intervening matter, providing a direct view into some of the most extreme events in the universe. These instruments will also help identify intermediate-mass black holes, a category that remains poorly understood. By detecting mergers involving these elusive objects, scientists hope to piece together the puzzle of their origin and evolution. Now let's talk about the influence black holes have on humans. The study of black holes transcends the boundaries of astrophysics, delving into the realms of philosophy, imagination, and societal impact. These cosmic enigmas not only redefine our understanding of space and time, but also serve as a source of fascination, inspiration, and education for humanity. Their profound influence reshapes the way we perceive the universe. Recently, scientists have found how black holes redefine space and time. Black holes are not merely astronomical objects. They challenge our very understanding of reality. Central to this is their ability to warp space and time, a concept rooted in Einstein's general theory of relativity. The intense gravitational field of a black hole bends spacetime to such an extreme degree that time slows down near its event horizon, a phenomenon known as time dilation. For an observer approaching the event horizon, time would appear to slow infinitely, effectively freezing at the boundary of the black hole. This mind-bending idea redefines our perception of time as a linear, universal constant. At the heart of every black hole lies the singularity, a point where space-time curvature becomes infinite and our current understanding of physics breaks down. Singularity forces us to confront the limits of our knowledge and pushes the boundaries of scientific inquiry. It presents a profound philosophical question. If the laws of physics as we know them cease to exist in such extreme conditions, what does this reveal about the nature of the universe? Black holes compel us to rethink a bit not only space and time, but also causality, determinism, and the fabric of reality itself. Now, real-world impacts of black hole studies will be discussed. While black holes are often seen as distant and otherworldly objects, their study has tangible impacts on education, research, and public engagement. Black holes are a powerful educational tool. They captivate students with their mystery and complexity, sparking interest in physics, astronomy, and mathematics. The study of black holes introduces learners to advanced concepts such as relativity, quantum mechanics, and gravitational waves. By tackling these topics, students not only gain scientific knowledge, but also develop critical thinking and problem-solving skills. Moreover, the excitement surrounding black holes can inspire the next generation of scientists. Iconic moments, like the first-ever image of a black hole captured by the Event Horizon Telescope, demonstrate the power of collaboration and innovation. These milestones serve as a reminder that science is a dynamic, ever-evolving field, encouraging young minds to contribute to its progress. But why do we study it? It is studied because of humanity's fascination with the unknown. Few phenomena in the universe captivate the human imagination as deeply as black holes. They represent the ultimate unknown, a place where light cannot escape, where time stands still, and where the rules of physics dissolve. This mystery is inherently compelling, feeding our innate curiosity and desire to explore the unexplored. Black holes often feature prominently in science fiction, serving as plot devices that explore themes of survival, exploration, and the limits of human understanding. From movies like Interstellar, which vividly portrays the effects of time dilation near a black hole, to countless novels and TV shows, black holes have become cultural symbols of the vastness and mystery of the cosmos. They inspire not only scientists but also artists, writers, and thinkers, highlighting the interconnectedness of science and culture. More than just cosmic phenomena, black holes embody humanity's relentless pursuit of knowledge. They push us to ask fundamental questions about the universe. How did it begin? What lies beyond the observable? Could black holes hold the key to understanding the multiverse? The quest to answer these questions underscores our drive to expand the horizons of human thought. One of the most significant real-world impacts of black hole research is its ability to engage and educate the public. Black holes provide a gateway for people to connect with science, fostering curiosity and wonder. Thanks to modern technology, complex concepts about black holes can be visualized and explained in ways that are accessible to non-experts. From documentaries to interactive apps, black holes have become a central theme in science communication. Public fascination with black holes also highlights the importance of funding and support for scientific research. By capturing the imagination of millions, black holes serve as a reminder of the value of exploration and discovery. They demonstrate that understanding the universe is not just about answering questions, but also about inspiring and wonder in the world around us. In every sense, black holes challenge us, scientifically, philosophically, and imaginatively. They force us to confront the limits of our knowledge while inspiring us to push beyond them. Black holes are not just objects in the distant cosmos. They are gateways to understanding the deepest truths of existence and the infinite potential of human curiosity. Now let's discuss about how black holes' disks shine. When matter falls toward a black hole, it doesn't just plunge straight in. Instead, it forms a swirling disk around the black hole called an accretion disk. This disk is made up of gas, dust, and other materials. All of these heat up and releases enormous amounts of energy. Artists often show black holes as simple, dark spheres hiding part of the disk behind them. But in reality, the black hole's intense gravity bends and distorts the light from the disk. This creates a mesmerizing and complex image. Friction within the disk causes the material to lose energy. Then the gas heats up to incredibly high temperatures, emitting vast amounts of electromagnetic radiation, mostly X-rays. This process is one of the most efficient ways to convert mass into energy in the universe. In fact, up to 40% of the mass of the material in the disk can be transformed into radiation. For comparison, nuclear fusion converts only about 0.7% of mass into energy. Now let's talk about X-ray binaries. X-ray binaries are binary star systems that emit most of their radiation in the X-ray part of the spectrum. These systems typically consist of a compact object like a black hole or neutron star. As the compact object pulls material from its companion, the material forms an accretion disk and emits X-rays. By studying these systems, astronomers can learn about the nature of the compact object. If the compact object emits signals that can be traced directly back to it, then it is not a black hole. However, the absence of such signals doesn't rule out a black hole. It could still be a neutron star. To determine whether the object is a black hole, scientists study the companion star to estimate the compact object's mass. If the mass exceeds the maximum mass of a neutron star, the object is a black hole. The first strong candidate for a black hole was discovered in 1972 using this method. Now let's discuss about what black holes teach us. Black holes, perhaps more than any other celestial phenomena, challenge the way we perceive the universe. There are paradoxical entities where the known laws of physics break down, yet their existence is rooted in the very principles that define those laws. To study black holes is to confront the edge of human understanding, where certainty dissolves into mystery. At their core, black holes embody the idea of extremes. They represent the densest states of matter, the strongest gravitational pulls, and the most warped fabric of spacetime. These extremes challenge us to think beyond our everyday experience. For instance, the notion of the event horizon, a boundary beyond which nothing, not even light can escape. It forces us to consider the limits of observation. What lies beyond the event horizon is a question that may forever elude human inquiry, leaving us grappling with the concept of inaccessible truths in a universe we strive to understand. Philosophically, black holes symbolize the duality of knowledge and ignorance. While they are products of rigorous scientific study, they also embody the unknown. This duality reflects our own pursuit of knowledge. Every answer we uncover leads to new questions, and every frontier explored reveals further horizons yet to be reached. Black holes remind us that science is not about achieving ultimate certainty, but about embracing the endless journey toward understanding. Black holes also compel us to rethink time and space, the very scaffolding of reality. Near a black hole, time slows down to a crawl, compared to the experience of an observer far away. This relativity of time highlights its malleable nature, a concept far removed from the linear, immutable way we experience it in daily life. Philosophically, this invites profound questions. If time is not absolute, how does this reshape our understanding of existence itself? Moreover, black holes prompt us to consider the fate of information. The information paradox, a question of whether information swallowed by a black hole is lost forever, touches on fundamental issues of determinism and the nature of reality. If black holes can destroy information, what does this mean for the predictability of the universe? And if they cannot, how does this reshape our understanding of entropy and the arrow of time? These questions, while deeply technical, are also profoundly philosophical, resonating with humanity's age-old search for order and meaning in the cosmos. On a more existential level, black holes offer a humbling perspective. They remind us of the vastness and power of the universe, of forces so immense they can consume stars and warp the very fabric of space and time. In the face of such grandeur, human life can seem fleeting and insignificant. Yet, it is precisely our ability to ponder such questions, to investigate phenomena as enigmatic as black holes, that affirms our significance. The same minds that map the structure of the atom can also probe the secrets of the cosmos, bridging the microcosm and the macrocosm, in a quest to understand our place in the universe. Black holes are also symbols of transformation. They emerge from the depths of stars, illustrating the cyclic nature of the cosmos. What seems like an end, a star collapsing into a black hole, is also a beginning, as black holes influence their surroundings, shaping the evolution of galaxies and potentially giving rise to new stars. This cycle of destruction and creation mirrors broader patterns in the universe, where endings often seed beginnings. Finally, black holes remind us of the beauty of the unknown. Their mystery sparks curiosity and creativity, inspiring not only scientists but also artists, writers, and dreamers. From the haunting depiction of black holes in movies like Interstellar to the poetic musings of philosophers, these enigmatic objects bridge the worlds of science and imagination. They challenge us to dream bigger, think deeper, and reach farther. In many ways, black holes are reflections of ourselves. Just as they pull in matter and light, they draw us in with their mysteries, challenging us to confront the limits of our understanding. They force us to reckon with the unknown, to push the boundaries of what is possible, and to find meaning in the quest itself. Through black holes, we learn that the universe is not just a collection of stars and galaxies, but a boundless expanse of questions waiting to be explored.